My name is JC Beyler. I work at Google, and I am the lead for the Tsan project in Java. And with me is Mon and Arthur, who are doing a lot of the work of actually bringing Tsan to open source. Mon and Arthur have both been at Google for, I looked, 2 years and 2 months for Arthur, and 2 years and 5 months for Mon. Mon is one of our GC experts with Wissam in the back over there. And loves runtime. And Arthur has been doing a lot of release work and testing for the JDK and has also been interested in runtime. Basically, the high-level goals of the Tsan project is let's see Java for everyone. And we've tried to actually work on making this open source and really available. We want to build a feature totally in the open, so we're taking what we have internally and trying to push it to the open using the open JDK mailing list to show what we're doing. And where the mailing list is Tsan dev, so if you're interested in what we're actually pushing forward, join that list and follow what we're doing. And basically our goal at the end of the day is to have no internal Google patches for this work, have it all in the open source and just be there, and it just works. The purpose of this talk, and I wanted to make it clear, we want to provide an update, but really what we would like is to get the feedback from the community, not automatically in our today, but I want to try to push people to use Tsan and actually contribute ideas. We have a lot of question marks where we're scratching our heads and we don't know what we're doing yet. So we'd love to have your opinion. We'd like to prefetch the design flaws to not come at the end of the day with a huge, massive rev and then go, oh, wait, no, we should never have done this way. So we're trying to avoid that. And so we're going to want to ask for design input. And we're going to start with a demo, to which I will awkwardly walk that way and wait till the end of the presentation.
All right, demo time. So we're going to try and see if Tsan can detect a super basic data arrays. So here we have 2 threads. They're both running this foo method up here 10,000 times, doing it concurrently. And they both add to this JVMLS variable. And if there's no synchronization, then this is racy because they can the reads and writes can overlap, it can interleave, and then you won't get an expected value that you want. So let's try compiling it, and then you can see I have this -xx Thread Sanitizer flag, which will turn on Thread Sanitizer. So compile it, run it, and then we get a stack trace. So you can see it says there's a read of size 4, that's the int, and there's a previous write of size 4, and these two are the racy reads and writes. And it even tells you where the thread was created. And then let's try and fix the race by adding a synchronize here. So now this should serialize any calls to foo. And then if we do the same thing, then wow, no race. Look at that. Okay. Yeah. Being a volatile, it will not detect a race because that's how volatile fields work. We'll talk about it a little bit later on. It is technically a race from like a user point of view, but we don't report those because we expect volatile to be used correctly, basically.
Okay, so how does the Java Tsan works? So before we introduce the Java Tsan implementation, we first talk about the LLVM Tsan, which is the algorithm and implementation that Java Tsan depends on. The LLVM Tsan is the stack of practice C and C++ data race detector. Basically, we have used it widely inside Google, and it has contributed for solving more than 10,000 C++ race bugs in Google. It has the algorithm used by the LLVM Tsan provides some nice properties. The first property is soundness, which means it never reports a false data race. The second property is dynamic completeness. That means for each execution, it will detect all the races in that execution. And that means it doesn't miss any true races in the execution. However, the both properties are actually limited by the implementation. So if the implementation has some bugs or have some incompleteness, the actual runtime may either report a false race or miss some races. For example, if you don't instrument some certain cases of synchronization, such as like synchronization is actually implemented in assembly, then the Tsan runtime does not know about that implementation, that synchronization, so it can miss a race. Fortunately, in most of the cases, the LLVM Tsan provides both of the properties, so it can detect the races correctly and soundly and completely. In order to detect the races, the LLVM Tsan runtime, which is embedded in both GCC and CLAN, it issues read and write instrumentations for all the memory accesses. And also, it needs to track all the happens before edges, which means it needs to instrument all the synchronizations. And there are also native library calls, such as like a memory copy and pthread create and joins. So these library function calls can either be a memory access by itself, or it can add some synchronizations. So the LLVM Tsan provides wrappers for these library calls in order to instrument them. So why do we use LLVM Tsan for Java Tsan? The main reason is for code convergence. Because the LLVM Tsan already implemented the actual data race detection algorithm, so we don't want to implement it again in the JVM. In addition, the LLVM Tsan provides callback APIs for Java, such as like a Java mutex lock, Java acquire, and Java reads, and Java move, like when Java moves the object. And the second question is, we may actually want to detect the races in native and JNI code. So the native and JNI code are user code, and they run together in the same process as the Java code. And if you have races in the C++ code and the native code, it may break all the nice properties that the Java provides you. So it's interesting that and it's important to detect all the native races together. And the challenge for using LLVM Tsan for Java Tsan is that we only want to detect races in users' Java code or native code, but not races in the JVM itself. In order to do that, we need to make sure we don't instrument the JVM's own C and C++ code. And also because the Tsan runtime provides wrappers for all the native library function calls, those can report races from the JVM itself. So we need to suppress races based on the stack frame. If it's called from the JVM itself, then we don't report the races. So the reason why we don't target the races in JVM itself is because it is hard. So data race is not actually well defined prior to the C++ 11 standard. And unfortunately, the JVM itself is not C++ 11 compliant. And fortunately, we will be moving towards that goal eventually. And the second reason is JVM has its own ad hoc synchronization and the workarounds. For example, it's basically re-implemented all the atomic accesses in the C++ standard library in a different way in the JVM, and it has its own like assembly functions that implement some kind of synchronization. And Tsan are not aware of all these synchronizations. So it will report false races if we attempt to use Tsan. It could be a future goal that we can try to use Tsan to detect races in the JVM itself, but it's not the current goal. So for how the Java Tsan works with the JVM, it's currently if without Tsan, there's a Bing Java launcher that you first execute, then it calls DL open, then that loads the libjvm.so, and which loads the entire runtime. Then you have a Java code like on the right-hand side, like it's a synchronizer block, and it performs the write to objects. And with Tsan, we link the native LLVM Tsan runtime with the launcher itself. It's because the Tsan need to do all the initialization at the very beginning of the program start. So you have to link it with the launcher. Then we instrument the libjvm.so with all the Tsan callbacks. So currently, Tsan only supports interpreter. So we add Tsan callbacks in the interpreter. And there are also certain cases in the JVM that you need to instrument, such as the class initializer, which established happens before in the Java code. So with all this implementation, a normal Java code will look like this. So after the Java lock acquire, you call a Tsan callback that notifies Tsan you acquire the lock on the Java side. So this like a Java mutex lock recursive. It doesn't acquire any lock. It just notifies the Tsan there's a lock acquired from the Java side. And also similarly for the write, it notifies the Tsan runtime there's a write as this G method ID and BCI, which provides support for the stack trace later. And finally, it unlocks the lock and notify Tsan about that. So for instrumenting synchronization in Java, we need to instrument all these possible places that can add synchronization for the Java code. That includes all the Java object logs and synchronized method and synchronized blocks, and some JVM-TI raw monitor logs that can use native logs to protect the Java accesses. And there are some acquire and release semantics in the JVM that established happen before for Java code. A good example for the last case is the class initializer. When you initialize a class, you actually establish happens before from the class initializer and the actual use of the class field. And for example, it's like if you have a synchronized block, then you need to add the Tsan callback after the lock acquire and notify about the address of the lock. And also before releasing the actual lock, you need to notify Tsan about the unlock. So that's the instrumentation for the synchronization.
Okay, so we've instrumented synchronization. Now we have to tell Tsan about the actual memory accesses. That's where the races are. So one thing to know is in Java land, only fields and array accesses can be racy. Other things like reading and writing from the stack, they're all local to a thread, so those can't be racy. So we only instrument these. The instrumentation order, so for example here, if you can add the instrumentation before or after the actual read or write, as long as it's correct relative to other synchronization. Mon has a paper on this. It's kind of hard to reason about, but yeah. So if you look at the synchronization itself, what we do is we give the size of the read or write, whether it's a read or write, the address of the variable, and then the current PC. And volatile fields. So what I said in the previous slide, those are all for normal fields, but volatile fields aren't racy according to the Java memory model, and they actually establish their own synchronization. So if one thread writes to a volatile field and another thread reads from it, then there's a happens before relationship between those two threads. And how we tell Tsan about that is we model it as a release and acquire. So you can see there's a release and acquire in the instrumentation there. And as opposed to the previous normal fields where instrumentation order doesn't matter, it does matter here because, again, Mon has more papers on this sort of stuff. But the contents of variables can affect synchronization later down the line, and that can affect what Tsan thinks is going on. Very, very high-level view of that. So sometimes we have intentional races. So for example, string.hash code is an intentional race where it's initially set to 0, and if you ever call string.hash code, it will calculate the hash and then store it to the hash field. And multiple threads can do this at the same time. And technically it's a race, but it's okay because you can only ever see either 0 or the hash. So in cases like these, we want to tell Tsan that we know there's a race here, and just don't report anything on here. So we have an annotation that you can add to a field that will basically tell, we will not add any synchronization for it if it's a primitive. Sorry, we won't add an instrumentation if it's a primitive. And if it's a reference, so if it's like an object or something, then we actually treat it as volatile because if there are fields in that object that if a thread reads a lazily initted object and then it reads a field of that object later on, then that could be considered racy. Tsan could think that's racy. And so there's an example of this like an abstract version of string.hash code. So we would add the lazy init on the field there.
Okay. So one key difference from LLVM Tsan and Java Tsan is that Java has garbage collections. So you need to notify how the objects are allocated and garbage collected and moved. And in order to that, currently Java Tsan implementation uses a naive approach, which at each allocation you add the object to a global hash map, and during a GC you iterate through that hash map and treat all the object references as weak roots. So this is a pseudocode of how this works. So during allocation, after the allocation, you add the pointer to the global hash map, then you notify Tsan runtime about this allocation. Then during a GC, it iterates each entry in the hash map, and if the object is alive, then you call the just pointer closure, which could move the object. Then you notify Tsan about this movement for the object. And if the object is not alive, then you notify the Java Tsan. It has freed the objects. So a better approach, maybe you can, if during the GC, when the garbage collector moves the object, you just call the Tsan Java move at that point. Then it's better. You don't need to track all these allocation and stuff. However, that does not solve the other problem is that you need to call the Java Tsan Java free, which is you tell the Tsan runtime to free the metadata for the race detection on that object. So because that's how Java garbage collection works, when it's doing a garbage collection, you only find all the live objects. You cannot directly find all the dead objects. So and now you need to call the Tsan Java free for all the dead objects. So that's the problem.
Okay, so Tsan thinks there's a race. So now what do? You have to tell the user somehow that there's a race and you want to tell them where it is. So we do that in the form of a stack trace. And one thing is that every time you enter a method, we tell Tsan that we've done that. And from the caller, we give it the JMethod ID and the bytecode index of the current location. And then Tsan keeps track of that internally. And then when we want to symbolize a frame, then Tsan will call back to libjvm.so. It'll give it a JMethod ID and a bytecode index, and then the JVM knows how to symbolize that, and then it'll return back a method name, file, and then a line number. So for native races, as Mana said, we do want to also keep track, report native races. And this is actually the initial Google goal, because we have lots of native code, and even if native races are very, very, there's undefined behavior and bad things can happen. So native races are worse than Java races. So initially, actually, we did this, we instrumented synchronization on the Java side to prevent false positives that if we didn't see the synchronization on the Java side, we would report as some false positives. And as Mana said, if you compile your code correctly, you can have the Tsan instrumentation in your native code, and then also, if you turn it on in Java land, then Tsan just knows about all memory accesses from C++ and Java, and then it can do whatever it has to. So for example, this is some JNI code. This is pulled from one of our JDirect tests. You can see that it'll even give you the stack trace for a native race. There's a write and two writes of size 4 there.
Okay. Before talking about the actual performance number, the disclaimer is that Tsan is completely not optimized for performance, and it's never designed to be run in production. It's a pure diagnostic tool that you run during test. So that's why we run a couple benchmarks, and the baseline for the performance is interpreter only, and the Tsan incurs about like 3 to 9 times execution time slowdown, and the memory overhead is about 1.5x to 4x. So that's the basic idea of why it's very slow and not suitable for production.
Hello again. Hi. We have a lot, or I should say a few, unresolved issues that we really want to have community feedback upon. One of them, for example, is actually importing the whole Tsan code that's in LLVM into OpenJDK. There are advantages of being able to compile it statically. That's the way it's done for LLVM and done for GCC, though GCC does a little different thing. But we'd have to resolve licensing issues, and I'm not sure that from a maintenance point of view, OpenJDK would want to import all Tsan. But if I could use my powers of explaining why this would be useful and convince you all, it actually would be a useful thing to do. So I'd like to figure out really why we would not, and then we can move out this topic and just bar it out.
What's the license?
I believe it's Apache compatible. It's a
Non-starter.
so actually the thing is this is where I got confused as well. It's included in GCC. So they actually have a license that is compatible with GPL
Okay,
somehow.
let's not rat hole into this now.
Yeah, hence
Happy to chat about
we'd
it.
have to resolve licensing issues, and I'm not a lawyer, and I generally stop there. I'm just confused why it got included into GCC and how they made that happen. Yeah. The second big question really that becomes more an adoption for later is when you are a library user and you want to have, for example, like the hash code calculation, and is our lazy init annotation a correct one? Like, will it work? Is it acceptable? And, what would we do? We like it, evidently, but I'd like to get the community feedback about that annotation. There is a usefulness to having such an annotation. What does it look like at the end of the day when we want to actually try to push this to mainline would be a really good one to have. How important is performance? Evidently, we care about performance. We don't want things to be way too slow. But on the other hand, adding more code to make this work in C1, C2 grawl, when really from a maintenance burden, you probably don't want to hit those technologies with more noise and more maintenance burden. You might want to say, well, why don't we just first wait and do an interpreter version first? Push that in first. And then if there really is a need for it or a requirement, then maybe do a follow-up piece of work in a follow-up JEP. That would be the line that I would follow, but again, I'd like to have opinions before we start pushing something forward at some point, and find out, no, we really need that support. And have a separate bin or Tsan Java launcher.
I'll talk about it. So the problem is that currently the Tsan is a build time option and a runtime option. And eventually, if you want to ship Tsan in a binary form, then you need to always enable that build time option. However, if you enable that build time option, you always link the Tsan runtime with the bin Java launcher currently. So that is a bit unacceptable for end users, because every time you launch a Java code, you load all the Tsan wrappers. So a possible solution is you add a separate launcher that has the Tsan runtime linked in. And when the user wants to run the program with Tsan, you use a separate launcher. Yep.
And because things are still not finished with unresolved issues, JVM-TI callbacks actually is an interesting case where a callback, the user thread or Java thread that's actually doing that callback gets sent what it wants to do to an event queue that the VM thread picks up and then does itself. But now the VM thread is a different thread that is doing a callback back into user code, handling potentially user data structures. And so you get an interesting race here where your Java thread has been paused so that the VM thread can do its work, but there's a race, right? It's tricky because the ports that actually passes via safe points there are various ones. And I'd like to have a conversation at some point, if someone's interested, about runtime, to figure out really what are the minimal changes required to get all of those correctly done. I like to do it evidently in the open, so if someone wants to talk to me about it, I would love to know, because I tried and hit a couple of walls on it. The newer features, unsafe and var handles, we actually have to start thinking about them and handling them if we want to have full support, and so those are tricky parts as well, right?
So we sort of handle unsafe a little bit right now, but we don't handle var handles and any of the newer stuff.
And then the final one is better final fields and finalizer implementation, which Arthur will give a word, but really if we look at the stick figure of Martin, it's complicated, right?
So final fields, currently we just ignore them. I think there's more that needs to be done if you really want to follow the Java memory model.
But it's complicated?
But it's complicated, yes, it's complicated.
Yeah.
And then for finalizers, I think we draw a happens before edge from all the current threads to the thread running the finalizer, and we might miss some races that way. But I think that does cover cases where, like, if you run finalizers concurrently, then there might be races between those. So
if some people in the room want to have interesting conversations that potentially will give you headaches, we'd love to talk about these topics. The conclusion of this is our OpenJDK Tsan repository. The demo you saw is what is available already in the open entirely. It contains the base implementation for the interpreter support. It uses the LLVM Tsan library, like we said, and we have our own JTReg test suite that we actually use and maintain in the open, so we can show that we are not regressing on ourselves, but also able to show what is currently supported. There clearly, as I hope I've shown, are some unanswered questions that I would love to have conversations with you all throughout these next couple of days to know who would be interested at least in talking about this. And so basically, please play with Tsan. Please try it out if you want. It is usable with all the caveats that we've said, all the stars and all the random conversations. We have our documentation that says how to download it, install it. And then basically you can try it out and start complaining to us that it doesn't work, and we would love to hear that.
And it's used internally at Google. It's been used for a while by a couple teams, and it seems to work.
A while being a couple of years. So I will already open the floor for questions if there are, and then I will, again, awkwardly and without any problems put back, please play with Tsan. And now, are there any questions?